In this video, we'll talk about temperature as it relates to artificial intelligence. Obviously, it is not the kind of temperature that regulates whether you feel heat or you feel cold. It is temperature that determines whether generative AI is creative or re or should I say redundant now? Or monotonous, maybe I should use that word. So why temperature makes ChatGPT creative? That's what we are looking at in this video. So by the end of this lesson, you should be able to explain why large language models generate text probabilistically rather than retrieving fixed answers. I mean, we've talked about that in an earlier video. I'd already talked about the fact that ChatGPT is just is a probability machine. Understand the concept of sampling and randomness in text generation. Derive and interpret the temperature scaling equation. Explain how temperature affects probability distributions. Implement temperature scaling in Python. Compare outputs at different temperature values. And understand practical applications of temperature in large language model generation. Then understand how temperature interacts with top K and top P sampling, which we also saw in some videos before now. So let's talk about the nature of language models. So a common misconception is that ChatGPT knows the next word in a sentence. It doesn't really know, like we've established previously. In reality, a language model does not retrieve a stored answer. Instead, it estimates, given all previous tokens, what is the probability of every possible next token? So that is some kind of Bayesian statistic happening there. So at every generation step, the model predicts probability distribution over its entire vocabulary. For example, consider the prompt. The capital of France is, internally, the model might estimate the following. So it tells you maybe Paris with probability 0.93, Lyon 0.03, Marseille 0.01, London 0.01, Berlin 0.01, Tokyo 0.01. Notice that if you sum up all the probabilities, right, that summation from I equals 1 to V of all the probabilities, PI, everything goes to 1. If you add up everything here, you get 1. Where PI is the probability of token I. So PI, probability of token 1, token Paris 0.93, Lyon 0.03, and so on. And V is the vocabulary size. Here, the vocabulary size is 1, 2, 3, 4, 5, 6. In reality, the vocabulary size can be tens of millions, whatever. So this probability distribution is called the next token distribution. Now, the model repeats this process after every generated token until a stopping condition is reached. Maybe you say, you just give some limitation within which you want your result. So then let's talk about tokens and not words. Large language models generate tokens, not complete words. We are focusing on ChatGPT, right? So we are looking at why temperature makes ChatGPT creative. And ChatGPT is a very good example of a large language model. So large language models generate tokens, not complete words. So a token may be a whole word like Paris, part of a word like maybe par on one side and is on the other side. Then punctuation like comma, full stop, and all that. White space, maybe my space name. So the space in between is also part of a token, or even multiple short words. For example, unbelievable can be broken down into unbelievable, and that may be represented as three separate tokens. So that it's one word, but it's given as three separate tokens. Generation proceeds one token at a time. So in generative AI, so one token at a time is generated, and that's why if you follow how when you prompt a generative AI, how the results come, you see that they don't come all at once, they just come one after the other like that. So we have, for instance, you have your prompts and you have prediction probabilities, and one token is chosen and then it is added, and another prediction is done, another token is chosen, and the process is repeated until you get the answer to your prompt. So this iterative process is called the auto-regressive generation because each new prediction depends on all previously generated tokens. So the whole Bayesian statistical idea. So now the question then goes to ask about sampling. So what is sampling? Once the model predicts probabilities for every possible next token, it must decide which token to output. So this decision process is called sampling. So just like we asked here what the capital of France is, and we have all this. So sampling is now the process of choosing. I mean, the highest probability is 0.93. So do you choose Paris just because it has the highest probability, or you may end up choosing Berlin, whatever. So that's the process of sampling. So once the model predicts probabilities for every possible next token, it must decide which token to output. So this decision process is called sampling. Sampling is therefore the algorithm that converts a probability distribution into a single selected token. So there are several sampling strategies, each producing different behaviors. The simplest strategy is greedy sampling, while more advanced strategies include random sampling, temperature sampling, top K sampling, top P nucleus sampling, and beam search. Temperature modifies the probability distribution before sampling occurs. So greedy sampling simply means pick the one with the highest probability, which is pari in this case. So following greedy sampling, the pari will automatically be the answer. But there are some cases where we have more nuanced scenarios. So, and that's why greedy sampling may not always be. If you always use greedy sampling, right? The answer will be our answers will always be deterministic, right? But because sometimes creativity may be required, other forms of sampling may become useful. So greedy sampling always select the token with the highest probability. Suppose the predicted probabilities are Paris, Lyon, London, and Berlin. So it just picks Paris. So the greedy decoding always chooses Paris because that's the highest probability. And the advantage of greedy sampling includes the following. It is deterministic. So highest probability means that you pick that. Then it is repeatable. So and then it is stable. It is often accurate. The disadvantages include the fact that it is repetitive. So if you are in a situation where you want creativity, greedy sampling won't do the job because creativity will mean that greedy sampling will mean you always pick the same results instead of varying it. There are some scenarios where varying the answers may be very important. Then another disadvantage is that it lacks diversity because it just goes for the highest probability and it may repeatedly produce the same phrases and it can become trapped in locally optimal choices. So, I mean, maybe there are better choices elsewhere, but because you just are interested in the highest probability, you just stay there. The random sampling now, instead of always choosing the highest probability token, we can sample according to the predicted probabilities. Imagine a roulette wheel where each token occupies an area proportional to its probability. So like Paris 0.9, Lyon 0.05, London 0.03, and Berlin 0.02. Most samples, of course, will produce Paris, but occasionally you can see something like Lyon. Lyon will be selected, and very rarely Berlin may appear. This randomness introduces diversity while still favoring highly probable tokens. So, I mean, Paris will come up many times, and Lyon will come up, a few times, and London and Berlin. So, of course, and that is why you always have that warning that AI can make mistakes so that you don't. So that's why when you are getting a result from AI, you want to also be sure. You want to cross-check with other facts or the knowledge you already have to be sure that you're not being misled. Now we go on to the idea of temperature, which we are here for. So suppose the model predict the following probabilities for the next token. Say Paris 0.9, Lyon 0.06, London 0.03, and Berlin 0.01. Even if you perform random sampling, the model will almost always generate Paris because it already has an overwhelming probability. Sometimes, however, we want the model to be more creative. So creativity is what brings up the idea of temperature. So we want the model to be more creative, more exploratory, less repetitive, or more willing to consider alternative words. For instance, maybe you're operating in a context where you're not just asking for the capital of France. I mean, the capital of France is always Paris, right? But maybe in a situation, you want to say something like, "I live in Japan." Or instead of I live in Japan, you can also say I stay in Japan or I inhabit Japan. You want that creativity sometimes. So this is exactly what temperature controls. So you may want a more willing, or you may be more willing to consider alternative words. So temperature modifies the probability distribution before the sampling step, right? So rather than changing what the model knows, temperature changes how confidently the model chooses among the available options. So think of temperature as a creativity knob. So low temperature means conservative decisions. High temperature means adventurous decisions. Conservative decision means you always conservative decisions will tend towards greedy sampling. They choose the token with the highest probability. But high temperature will mean, you have the probabilities are not clearly marked. Like you have a fairly equal spread, and then you can pick any option almost likely. I mean, with almost the same level of assurance. So importantly, temperature does not add knowledge to the model. It only changes the probability assigned to candidate tokens. That's what temperature does. Temperature enhances creativity when it's necessary. So intuition behind temperature now. Imagine asking several students the question, what is 2 plus 2? Student A uh, says I am 99% confident the answer is 4. So the probability distribution is this. So the answer is 4, 0.99. The answer is 3, 0.05. The answer is 5, 0.005 also. So this resembles a low temperature language model because here the answer clearly favors 0.99. On the other hand, student B is telling you, oh, I think it's probably 4, but I am less certain. And the probability that it's 4 is 0.7, probability that it's 3 is 0.15, 5 is 0.15. This resembles a higher temperature model because now the probability is not as sure, as certain as what you have here. So both students possess the same knowledge for sure, and the difference lies in how strongly they prefer the most likely answer. Okay, so temperature changes confidence, not knowledge. So it is just temperature is all about confidence. Now, where do probabilities come from then? Neural networks do not directly output probabilities. So instead, the final layer of the transformer produces logits. A logit is simply an arbitrary real valued score. So it's just like, oh, okay, what is the capital of France? And then Paris, it just assigns it a score of 8, Lyon a score of 4, London a score of 2. Now, in this case, take note that logit is not probability. So if you add up 8, 4, and 2, you don't get 1, right? But from logit, you get probability. Logit is not probability. Logit are arbitrary real value scores assigned to tokens. And then these logits are then transformed into probabilities. Then we can make decisions. So notice that these numbers are not probabilities and they can be negative even. And they do not sum to 1. So, and they have no upper limit. So logits can be any negative number, any positive number, no matter how small or big. So to convert logits into probabilities, we use the softmax function, which I think we saw in a video before, and I think we're still going to see it in future videos when we talk about the idea of attention. Yeah. So I introduced attention in the introductory video to this playlist. So the softmax function transforms arbitrary real numbers into a valid probability distribution, which is then used for other for the whole sampling thing. So the softmax function is as follows. Suppose the logits, if you have logits assigned to tokens as Z1, Z2 up to Zn, the probability of token I is computed as Pi, which is exponent Zi all over summation from j equals 1 to n of exponent Zj, where Zi is the logit and Pi is the result probability from the logit. So softmax has several useful properties. Every probability is positive. All probabilities sum to 1. Even when all the z, any of the z is negative, by the time you take the exponent, it becomes something positive. And by the time so this normalization, what you have down here is you normalizing it to make sure that the probability, it follows the rules of probability. So all probabilities sum to 1. Large logits receive exponentially larger probabilities. So because of the exponential function, even small differences between logits can produce very different probabilities. So this is why one token often dominates the distribution. For example, let's compute softmax here. So suppose the model output the logits Paris 8, Lyon 4, London 2. First, compute the exponentials. You have e raised power 8, which is 2,980.96. E raised power 4 is 54.60. E raised power 2 is 7.39. So we compute the exponentials. Then the next thing is you can then have the denominator becoming the sum of all this now. So that'll be E8 plus E4 plus E2. That's 2980.96 plus 54.60 plus 7.39. And that's all of that will be 3042.95. Therefore, the probability of Paris now, so everything now becomes probability. Probability of Paris will now be the exponent of the logit, that's 2980.96 all over the summation, and that's approximately 0.9796. Then for Lyon, 54.60 all over 3042.95. For London, that's 7.39 over 3042.95, like that. So 0.9796, 0.0179, 0.0024. Almost every sample will therefore produce Paris because I mean, so the logits, the probabilities will usually almost always go the way of the logits. So here now, we can write a code for all of that. The probability code computes the softmax probability. So if you add all the probabilities as usual, you get 1. So the following code computes the softmax probability. So for the logits, you have 842 exponential of the logits. You have that. Then probabilities will be exponent of the logit divided by the sum of the logits. So if you do that, you get the probability 0.09796, like we got up there. Then for 4, you have 0.0179253, and so on. And the other one, for logit 2, you have 0.0024, which is 0.002486, So observe that when you add it all together, you get 1. So the probability sum to 1 as required. So then we go to 16.10. Now we have the temperature equation. Now, temperature modifies the logits before applying softmax, right? So instead of computing Pi is softmax Zi, we compute Pi is softmax Zi over T. So that's where the temperature then comes in. So PR is the softmax of the the logit over the temperature before we now convert to probability. So T is temperature, Z is the original logit. So the only difference is the division by T. So when we did the softmax computation with the direct with logit directly, we just did that. But here, before we do the convert to probability, we need to divide first by the temperature to add some creativity. So the only difference is the division by T. Despite being a simple mathematical operation, this dramatically changes the resulting probability distribution. So if you try that on the same thing we did before, you see the difference. So imagine temperature equals case one. If the temperature is equal to one, so the situation you have is exactly what you had, like default behavior like before. So if T is one, then Zi over one is Zi. So therefore, softmax of Zi over one is still softmax of Zi. So in that case, temperature one doesn't change anything. So nothing changes. So temperature equal to one is therefore considered the default behavior. So the original probability distribution is preserved exactly with a temperature of one. Now, how about a temperature of T less than one rather? Suppose temperature is 0.5. So the logits are 842 become 8 over 0.5, 16, 4 over 0.5, 8, 2 divided by half, 4. So the differences between the logits become much larger, right? 16, 8, and 4. So as a result, the largest probability becomes even larger and the smaller probabilities shrink. So the distribution becomes much sharper, and this causes the model to behave more confidently. So low temperatures therefore produce deterministic outputs, less randomness, higher consistency, and reduced creativity. So these are three scenarios for temperature. Temperature equals one, temperature less than one, and now temperature greater than one for high temperature. Suppose T now is two. So the logits become 4, 2, and 1. Like the original logits are 8, 4. To divide each one by 2, you have 4, 2, 1. Now the logits are much closer together, as you can see. So when we divided by 0.5 before, so the logits are wider apart. Here they are closer together. So now the logits are much closer together. Consequently, the largest probability decreases, the smaller probabilities increase, more candidate tokens become competitive, the probability distribution becomes flatter, higher temperature produces higher temperatures therefore produce more diversity, more exploration, more surprising word choices, and increased creativity. Extremely high temperatures, however, may also reduce coherence. So let's implement temperature scaling in Python. So the following function implements temperature scaling followed by the softmax function. I mean, everything we've done before is just what this one is doing here now. So we have a function to, so we define a function softmax temperatures that takes in logits and temperature. So compute softmax probabilities after applying temperature scaling. Then we have the parameters logits array like raw out input. So see this. So here is just to define the function itself. So we have the scaled logit, that's logits over temperature, and then we now have scaled logits, that's scaled logits minus uh maximum of the scaled logits. And then we have the exponential exponents of the logit. This is numerical stability trick here in line 24, which we didn't talk about before now. So if you run this now, uh so yeah, the function is already set. We are going to use it in the next place. So this implementation first divides every logit by the temperature before computing the softmax probabilities. So subtracting the maximum logits prevents numerical overflow when computing exponential. So this line 24 is for the sake of stability. So from the scaled logits, we now subtract the maximum of the scaled logits from each one. So here, imagine example using temperatures now, using different temperatures. Suppose the model predicts the logits 842. So the following Python code computes the resulting probability distribution for several temperatures. So imagine, you have your logits 842 for time. I mean, for temperature 0 0.5, 1, 2, and 5. We now have probabilities, soft max of temperatures, which takes in logits. We already defined the function as softmax, so you need to supply logits and temperature, right? So we have the logits now. You pass them as an array, and then you take the each. So you pass this 842. You take 0 0.5 for the first case, 1 for the second case, 2 for the second case, for the third case, 5 for the fourth case, and then you output the results. So this is a loop right here. So you print the temperature and print the probabilities and all that. So see what happens there. So this blank print is to create space for the next one. So with a temperature 0 0.5, you see you have 0.999, and then you have 0.00033. So, this one's way smaller, while this one is pretty big. So with temperature one, everything remains what it used to be. With temperature two, you can see the probabilities are instead of the 0.99, it's now 0.84. So, and this one that was smaller comes up a bit. This one that was really small comes up a bit more. And then with temperature five, you can now see that 0.99 initially becomes like 0.57. And this other one, which was 0.000 something, is now 0.25. So here now you have more. The probabilities are they are closer together. So observe that increasing the temperature spreads probability more evenly across candidate tokens. So increasing the temperature calls for more creativity. So to interpret the result, and the previous example illustrates several important observations. Temperature 0.5, almost the probability is concentrated on the most likely token. That's the first one, which is 0.99 something. And then temperature, the model behaves confidently in that case. For temperature one, the original probability distribution is preserved. For temperature two, alternative tokens become significantly more likely, and sampling begins to produce more diverse outputs. Then temperature five, it's even more serious. The probability distribution becomes much flatter, and the model explores many more possible continuations. Notice that no new tokens are introduced in this case. So temperature only redistributes probability among the existing candidates. So it's more like, okay, can we, because we want creativity, can we work on them and get different scenarios? So to visualize probability distributions, for instance, imagine talking about tokens Paris, Lyon, and London, and the logits are 841 with temperature 0.5, 1.2, blah blah. So we also do that looping, for all the for each temperature for the logits and all that. So for temperature 0.5, see, Paris gets Paris is outsizely favored. And then so temperature one now, Paris is of course still up there, but Lyon comes up a little bit and London is very tiny, almost invisible. Temperature two, you can see London is gradually coming. Lyon is bigger, London is coming up, and Paris is shrinking. And with temperature five now, you see Paris is even shrinks further, and these other ones come up. So this is useful in the case where I mean, of course, the capital of France is Paris, right? So, but there are situations where maybe you want synonyms or antonyms and things like that. So you want a bit of creativity right there. So as the temperature increases, the tallest bar becomes shorter, the smaller bars become taller. The probability distribution gradually changes from sharp to flat. You know, so what that means is for when you have uh less than one temperature, you have something like this. So this thing is tending towards a more particular value. But as you increase the temperature, so you begin to have, you know, things flatter, not quite like not like quite like the sharp thing you have. Yeah. So what does sampling actually mean then? So once the probability distribution has been computed, the model must choose one token. So suppose the probabilities are now after all the temperature, adding temperature and everything, Paris is now 0.84, Lyon is 0.11, London is 0.05. So sampling means selecting one token according to these probabilities. So this is analogous to drawing a colored ball from a bag where 84% of the balls are labeled Paris, 11% are labeled Lyon, and 5% are labeled London. So every draw is random, but tokens with larger probabilities are selected more frequently, of course, for obvious reasons, because probability is high. So if you do a random sampling in Python, then if you use the function numpy.random.choice, which performs probabilistic sampling. So imagine import numpy as np. So you have the tokens Parillion and London. Probability 0.8 for 0.11, 0.05. So for everything, for each thing in from 0 to 9, and that's in range 10, that's 0 to 9. So you just print what you can get. So that's 10 outputs. So if you run that now, so you see Paris appears more. In fact, Paris is appearing everywhere here. But if you do it again, so you have Leon coming up a little bit, and then you have, okay, because Leon has the next set of probability. So Paris is just dominant most of the times. So imagine if this is now 0.70, and then maybe this is 0.15, and this is also 0.15, so that everything adds to one, right? So now you see this two, but Lyon and London have more chances of showing up together. So you can see Lyon and London will come out around the same uh time. So, but Paris, of course, still dominant. So you have that randomness going on like that. So imagine, let's say this is now 0.20, whereas this is 0.10. Okay. So of course Paris still dominates like that. So yeah, let me take it back to what it was initially. Yeah. So Paris always dominates. So it doesn't mean that Paris will always appear, but it will appear the most of the times. Notice that Paris appears most often, Lyon appears occasionally, London appears rarely. So that's with the original 0.8 for 0.11, 0.05. So this behavior closely matches the specified probabilities. Now, simulating thousands of samples now. So if you simulate thousands of samples, sampling becomes much more intuitive when repeated many times with the same probabilities in place. So if you now do the samples, yeah, so the samples NP the random choice token size 10,000 p probabilities, and then you do the counting, and then in this case now it's hard to follow one after the other, so we can do some plotting. So if you now do 10,000 sampling now, so you see Paris is still up there, Lyon follows, and London can still be a bit more visible. So imagine make it like, okay, did I even run this? Let me run it now. Okay, yeah. But let me make it like 100,000. 100,000, it's even more visible. The more sampling you do, the more visible these things become. Okay, so you still have that kind of thing. So this one is like 100,000 samples now. But let me leave it back at the 10,000 samples. Yeah, so we have that. Because of the law of large numbers, the observed frequencies approach the underlying probabilities as the number of samples increases. So, why does higher temperature produce creativity then? Now, suppose the model predicts cat 0.6, tiger 0.2, lion 0.1, dragon 0.06, and spaceship 0.04. With a low temperature, the distribution becomes even more concentrated around cat. So, low temperature means less creativity. So the model repeatedly generated safe and predictable continuations. With a higher temperature, on the other hand, probabilities become more balanced. Now, so if you want creativity, you need higher temperature. So now tokens such as Dragon, Spaceship, and Lion have a much greater chance of being selected, like we saw with the case of Paris, London, and Lyon. So these unusual word choices can lead to novel metaphors, unexpected associations, imaginative stories, and even creative writing. Or it can clearly even be it can now be like a mistake. That's why AI can make mistakes. So, but of course, in the other context, it could be creativity. So creativity therefore emerges from exploring lower probability regions of the model's learned distribution. So, of course, the creativity here is not randomness, right? It is tempting to think that creativity comes from random guessing. This is not true. The language model never samples uniformly from vocabulary. Instead, it samples from a probability distribution learned during training. For example, if you have cat 0.6, tiger 0.2, lion 0.1, Dragon 0.06, spaceship 0.04. Even at high temperatures, the model is still much more likely to generate cat more than spaceship because cat is at the higher side of the spectrum, so to speak. So temperature changes relative probabilities, not the underlying knowledge stored in the model. So what temperature does is to give the underdogs higher chances. That's a layman's way of talking about that, right? So the exploration exploitation trade-off now. So exploration exploitation. So temperature controls the balance between exploitation and exploration. So talking about exploitation, the model repeatedly chooses the highest probability tokens. So advantages that you have consistency, reliability, and accuracy. But the disadvantages, in the cases where you don't want where you want creativity, such a thing it can lead to repetitiveness, predictability, and less diversity. So on the other side, for exploration now, exploration has a lot to do with creativity. So if you want consistency, you go for exploitation. If you want creativity, you go for exploration. So the model occasionally selects lower probability tokens. Now, for me, I have some my taste of music. My taste for music on YouTube, right? There are some go-to songs I have, but once in a while, I just allow myself to scroll through randomly. So in that process, I might just discover maybe there's somebody I've been missing out all the while whose music I really like. But there's no way I would know if I just stick to the ones I always like. So there's a place for exploring. Just check. You may not find anything you like, but who knows, you might just find something you really enjoy. So the model occasionally selects lower probability tokens. So advantages include diversity, novelty, and creativity. Then disadvantages can include possible mistakes, like I said before, reduced coherence, because now things don't make sense anymore. Because I mean, the capital of Paris is Lyon. That's wrong, but that's what a high temperature can cause. Reduced coherence, occasional nonsensical outputs, and that is why sometimes you get some answers, especially in the early days of ChatGPT. You you do something like five, maybe 16 combination three, and it's giving you wrong answers, and you have to correct it that no, this answer is wrong. So temperature therefore controls where the model operates along the exploration exploitation spectrum. So if you want exploration, stick with low temperatures. If you want exploration, sorry, stick with high temperature. If you want exploitation, stick with low temperature, because exploitation is associated with consistency and exploration is associated with creativity and diversity. Now, let's talk about temperature versus top case sampling. I think we've talked about this in a previous video also. Temperature modifies the probability distribution, as we know already. So, but top case sampling modifies the set of candidate tokens. Suppose the vocabulary contains following probabilities, say A, B, C, D, E, F, with probability 0.4, 0.25, 0.15, 0.10, 0.06, and 0.04. Now, if K is 3, only the three most probable tokens are kept. So if you are using top case sampling, that's and K is 3, it means you are interested in the top three sampling. So it means you pick the tokens with the highest probabilities. That'll be ABC in this case, right? So you now stick with ABC. So you have A now to be 0.40, B is 0.25, and C is 0.15. But then, of course, you see that this one doesn't necessarily add up to 1. So the remaining tokens are then, so all the C, D, E, F, I mean D, E, F, you throw them away and you focus on A, B, C. But you can see the probability distribution doesn't sum up to 1. So that's now an issue you have to deal with. So the remaining tokens are discarded, but then the remaining probabilities are then renormalized so that the summation of pi is equal to 1. So you renormalize using this value. So it's more like this total is 0.8, right? If you add this up, so 0.4 over 0.8. So A will now have 0.5. Then 0.25 over 0.8. B will have something, that proportionately. And C will now be something like that also. So, uh, so that's for top. So top case therefore limits how adventurous the model can become regardless of the temperature. So top case sampling helps to discard it's so that way you can remove distractions and focus on what really matters. That's the idea of top case sampling, right? So look at the example of top case sampling like I was demonstrating before. Suppose probabilities are the one just like what we showed before. Using k equals to the main probabilities are then 0.4, 0.25, 0.15. But if you add this, it's not 1. So you have to renormalize. You have to renormalize. So the total retained probability will now be 0.4 plus 0.5 plus 0.55, which is 0.80. So the new probability of A now will now be 0.4 over 0.8. That'll be 0.5. So you see the probability is higher. 0.25, that will now be 0.3125 higher. C now is 0.1875, which is higher than this. So you now note that D and F can never be selected because they were removed before sampling. So if the right answer was part of D and F, top three sampling would have removed that. Okay, but of course, it is also done with the assumption that the most probable answers are the ones with the highest probabilities. So most of the times that will be correct, but once in a while that may not be. So that there's top K sampling. Now we are talking about top P nucleus sampling. So top P sampling does not keep a fixed number of tokens, right? Instead, it keeps the smallest set of tokens whose cumulative probability is at least a particular value P. You have a probability target, and then any set of tokens that whose cumulative probabilities meet that target are retained. So that's slightly different from just selecting the top three or top five or whatever K value you have. So here now, if you have A to be 0.5, B 0.3, C 0.12, D 0.05, and E 0.03, the cumulative probabilities are, you know, so token A, B, C, D, E, F, A, B, C, D, E now. So probability 0.5, 0.80, 0.92. Now that's cumulative now. For instance, see, for A, that's 0.5. For B, that's 0.5 plus 0.3, that's 0.80. For C, that's 0.80 plus 0.12, that's 0.92. D, 0.97, and E, 1.00. So because everything adds up to 0. So these are the cumulative now. So you add them, keep adding them up. So if your P is 0.9, Okay, so if the value of P you have selected, that's the top, you now have a top 0.9 sampling or top 90% sampling in another manner of speaking. So in that case now, you see only A, B, and C fit into that because A is 0.5, B is 0.8, 0.9, of course C is 0.92, but I mean 0.9 lies still within this region. So in this case, A and B are retained. So you now have 0.5 plus 0.3 plus 0.12, which is 0.92. So tokens D and E are discarded in this case, and sampling then occurs only within the retained nucleus. So of course you have to resample too. So that's why it is called the top P top P or nucleus sampling. So we go on to talk about comparing temperature, top K and top P. Although these techniques are often used together, they control different aspects of generation. So for instance, if you talk about temperature, it controls probability distribution and it changes confidence. Top K controls the number of candidate tokens and it removes unlikely tokens. Top P controls cumulative probability mass and it keeps only the most probable nucleus. So a common decoding pipeline then is that you have logits assigned to your tokens and you have temperature scaling if you are interested in temperature. Then after temperature scaling, you now use softmax, which is which involves normalizing the the temperatured softmax if you like, and then you can then use top K or top P filtering, and then you can sample based on whatever criteria. So temperature changes how probabilities are distributed, but top K and top P change which tokens remain eligible for sampling. So it's like this ones they are reducing your stress. You don't want to focus on things that don't really matter. That's what top K and top P are doing for you. So while at temperature is increasing the possibility of creativity. So typical temperature settings can be as follows. The optimal temperature depends on the task, right? So how do you know the best temperature to use for each task? So for mathematical reasoning, the typical temperature is from zero point 0.0 to zero point 0.2. For programming, 0.1 to zero point 0.3 because programming now, different 10 people can write they can write different codes to get exactly the same result because there are nuances in how you can go about the coding thing. Then in translation you want some creativity, so you need low temperature. Question answering, you have zero point 0.2 to zero point 0.5. Summarization 0.2 to zero point 0.5. Technical writing 0.3 to zero point 0.5. General conversation 0.6 to zero point 0.8. Brainstorming 0.8 to 1.0. Story writing 0.9 to 1.2. And poetry 1.0 to 1.3. These are like typical temperature settings. So these values are guidelines rather than strict rules. They are not strict. So in your context, check what you are doing and decide how creative you want to get. So for poetry now, create as we go down the stream. So you see mathematical reasoning, the mathematical answers are fixed for the most part. Programming too like that. So as you go more and more creative, like you go all the way to poetry, you unleash your creativity. That's why you have temperatures. Even story writing, you have temperatures. It's fast starting from brainstorming, right? It's not nothing serious. You want to be as creative as possible at the level of brainstorming. You are not pinning down anything at that point. So these values are guidelines rather than strict rules, like I said, and different models may respond differently to the same temperature setting. Now let's look at some common misconceptions. Misconception one is that temperature changes the model's knowledge. Not at all. That is false. Temperature only changes how probabilities are redistributed before sampling, and that calls for creativity. Then misconception two is that higher temperature always means better creativity. That's another false. Of course, higher temperature helps creativity, but it doesn't always make it better. So very high temperatures may produce contradictions, hallucinations, repetitive nonsense, broken grammar, or even outright wrong answers, right? So creativity increases only up to a point, with temperature. So you want to be sure. So that's why you have to situate your temperature in a proper place where you have the balance of the creativity you want, and without going overboard. Then we have misconception three, which is the fact that temperature equals randomness. Not exactly. The randomness is always guided by the learning probability distribution. So temperature merely changes how concentrated or spread out that distribution does become. So we have end-to-end generation pipeline based on the things we've been learning. The complete generation process inside the modern large language model can be summarized as follows. You have a user prompt, so you prompt what is blah blah blah, and then your prompt is broken into tokens with the help of a tokenizer, and then you have transformer neural network working on all of that to assign them logits. That those are assigned values, and then you then have temperature scaling if you want. If depending on what kind of temperature you want. I mean, temperature scaling, we can put that as a standard because even if you want the status quo to remain, you just set it at a temperature of 1 to retain the status quo. Then you can then do softmax, which is normalization to get probability distribution. And then you can then decide if you want to do a top K or top P filtering. That's optional. It depends on what you want. Or you can, of course, do the regular, what's that thing called now? Do the regular greedy sampling. Just pick what the highest probability, and then you sample the next token. You pick the next token, then you append the token, and you repeat until you get all your results. I mean, or the system repeats until you get the results you want. So notice that temperature influences only one stage of this pipeline. That is the conversion of logits into a probability distribution before sampling. So in summary, temperature is one of the most important hyperparameters controlling text generation in large language models. The key ideas are large language models predict probabilities of every possible next token. Then the neural network outputs logits, not probabilities. Softmax converts logits into a probability distribution by that normalization process we had explained before. Then temperature rescales logits before softmax, right? So if you need to use softmax, so you have to divide the probability, the logits by temperature first before taking the softmax thing. Then low temperature sharpens the probability distribution. High temperature flattens the probability distribution. So low temperature sharpens probability distribution, leading to consistency, predictability. While high temperature flattens the probability distribution, leading to creativity and all that. And of course, each of them can go overboard for sure. Then sampling selects one token according to the resulting probabilities. So whether by the most common, the go-to one would be like greedy sampling. Just pick what has highest probability, except you now want to use top K or top P sampling. So creativity emerges because higher temperatures increase the likelihood of selecting lower probability, but still plausible tokens. Then temperature changes confidence, not knowledge, right? Temperature just changes the level with which you believe in something, not the knowledge itself. The modern LLMs often combine temperature with top K and top P sampling to balance diversity, coherence, and factual accuracy. So our key takeaways from this whole thing is as follows. Large language models generate next one token at next large language models generate text one token at a time by predicting probability distributions over a vocabulary. Then next, the raw outputs of the neural network are logits, which are transformed into probabilities using the softmax function. Then temperature modifies the logits according to pi equals exponent of zi over t. So if you need temperature, if temperature is 1, you just have exponent of zi all over the summation of that zj of over t. So this is the kind of normalization. Then lower temperature produce sharper distribution, leading to deterministic and consistent outputs. Higher temperatures produce flatter distributions, increasing diversity and creativity. Then sampling is the process of randomly selecting the next token according to the computed probabilities. Top K limits the number of candidate tokens, while top P limits the cumulative probability mass of candidate tokens. Then temperature, top K, and top P are complementary decoding techniques that allow practitioners to control the balance between accuracy, diversity, and creativity in large language models generated text. Understanding these decoding mechanisms is essential for effectively controlling the behavior of modern language models such as ChatGPT, Gemini, Claude, Llama, Mistral, and many other transformer-based systems. Okay, so in this case, because the process is pretty clear, I won't bother solving any of the problems like I always do. So I'll just flash the problems and get it over with. So the following exercises are designed to reinforce your understanding of temperature, sampling, probability scaling, and generation control in large language models, unless otherwise stated. Justify your reasoning and show all immediate calculations. So in case you don't understand how to proceed with anyone, go back to the notes and then you can have a way out. So here I'm showing 1 to 3. You can see questions 1 to 3 all. Then now you can see 4 to 9. 4 to 9. Then 10, you can see 10 to 15, 10 to 15. Everything 10 to 15 is here. Then 10, 16 to, okay, we saw 10 to 15, right? So 16 to 19, showing 16 to 19. And then the rest. Okay. So, I mean, it's quite straightforward. So, that's why I won't bother to solve any of the problems because it's just straightforward. So, let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, thank you very much for doing that. If you have not subscribed, why not go ahead and do that right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join. That gives you some special privileges that you will find when you click on join. Ultimately, don't forget to comment, like, and share so that more people can have access to great content I have going on here. Till I come your way again, keep doing maths right. Bye.